Hello and welcome back. In this video, we are going to start looking at Hebb's theory and how it relates to neural networks. So, in this very first video, let's look at who Hebb was. So, Donald Hebb, he was a neuropsychologist who worked on understanding how neurons work in our brain, and he has also written a book, The Organization of Behavior. So you can access it at Internet Archive. I'll put the link in the description below. So basically what he said was uh, that neurons in our brain that work together, the connections between them get stronger. So if you have heard the saying, neurons that fire together wire together, what it means is that if we have a neuron that consistently is stimulating another neuron, then the connection between that neuron and the other neuron uh, becomes more and more efficient. So that could explain why, if you keep practicing a certain task or certain skill, we get good at it eventually. And that is the analogy we are going to think about when we talk about neural networks. And just before we get there, here is a picture of neuron, biological neuron. So the neuron that we are going to think about is not going to be a biological neuron as you see here. Instead, we are going to say that this could be the input vector, and here would be our output vector. And the connection between the input and output is uh, sort of managed by weight matrix. Now, before we start looking at the theory, let's first clarify on a few things what is input in the context of Hebb's theory. So when we say input, you'll hear the words prototype, and you may also hear the words, let me just get thinner pencil if I can, wonder right here. So prototype or prototype vector or a pattern vector. And what that means is, unlike our regular ML inputs where we have columns, so column 1, column 2, that's our data, and then we have sample 1, sample 2, these are our samples. So uh, we say that this is feature. So if we are talking about rainfall, maybe this is rainfall, this is some city name, and so on. So these are our features. So this could be feature number 1, this could be feature number 2, and so on. And these samples, these are the data points. So data point number 1, data point number 2. So that's what we are used to thinking. But when we are thinking about Hebb's theory, or prototype vectors or pattern vectors, this is not what we are going to think. Instead, what we are going to think about is a vector that looks pretty simple with just values such as -1, or even going before that, it just tells us if positions of on or off. Let's just say that this is all we are going to think about when we uh, think about input vectors in case of this Hebb's theory we are going to look into in couple of videos. So the on can be represented by number or digit 1, off can be represented by digit 0. So the input vector in this case could be this, or we can represent on again with 1, but off we can represent by -1, again on by +1, off by -1. This could be again a different type of input vector. So this is we can say this is like a binary input vector. This could be bipolar, so it has +1 -1. And we could also have input vectors that are normalized. So let's say if we take the input vector, this one, and if we get the norm of that, so what we would do is take 1 square plus minus 1 square plus 1 square plus minus 1 square, and so that turns out to be 1 plus 1 plus 1 plus 1 equals square root of 4, that is equal to 2. So when we normalize this, essentially we are going to divide each of these by 2, and what we get then is a input vector, prototype vector or pattern vector that looks something like this: plus 0.5 minus 0.5. So in this case, although it does not say 1 or 0 or minus 1, this still is a pattern that is pretty easy to understand. This could be thought of as on, this could be thought of as off, and so on. So that's the first point. We would like to make sure that this is what we need to think about when we say input vector. So that's what this is. And in case of the neural networks that we are seeing, if you see me draw this box with r written below it, an arrow coming out of this saying that this is r by 1, this is the input vector. Here in this input vector, each, if we have these values, if I have the values 0 1 1 0, then each of these is, we can think of these as a feature, and this is our data point. So that's the sample, or that's the input. So uh, this, if we compare these two, here we have the data arranged as so row by columns. So in the row we have the sample, and columns we have the features. But in this case it's the other way around: we have features along the rows and the sample data point sample along the columns. So that is another thing you need to remember when we talk about input to these networks. So these features could be something like facial features. Let's say if we can have uh, the first feature 1, which says wears a hat. Then if the person wears a hat, then this is a 1. If the person does not wear a hat, it's a 0. Then does the person wear earrings? And if the person does wear earrings, it's 1, else it's a 0, and so on from here. So if there is a person has a beard, then it's 1, else it's a 0. And does the person wear glasses? If the person wears glasses, it's a 1, else it's a 0. So this is how we are going to think about input vectors, and you can swap these with uh, other other sort of ideas about what you would like to present as 1 or a 0. In context of Hebb's theory, we are going to look at a linear associator type of linear neural network, and with this we are going to think about a term called as a associative memory. And what this means is, think of a system that learns to connect one pattern with another pattern, and in such a way that when we show that system the pattern, this is the first one, it will automatically give us the second pattern out. And so how does it do that? It does that by storing the memory in something called as a weight matrix. And that's a beautiful part of this theory, is how does one store memory in a weight matrix. Think of the stored memory as a notebook. Imagine you have a notebook, and each time you get some information, you write it down in the notebook, and So if later on, if you have to find information about something specific from that notebook, you flip through the pages of the notebook and find that particular thing that you're looking for. And that is how, in a general way, the weight matrix would work, where the idea is that we try and store patterns in the weight matrix. So the question is, how can multiple memories be stored in just a single weight matrix? And that is possible because each memory leaves its own mathematical fingerprint inside the W in form of an outer product. So we could say that memory Q is, let's say, MQ, that could be written as TQ plus PQ. Sorry, not TQ, but TQ dotted with outer product with PQ transpose. And as we know, these both are vectors, and so the output of this is a matrix that is of the same shape as the weight matrix. And so the shape that we'll see, it would be something like S by R. And so the full memory store then for W is summation of Q equals 1 to Q. MQ is equal to M1 plus M2 plus all the way up to M2 all the way up to MQ. So each MQ affects only the weights between the neurons that are on. And remember, here the new we are dealing with only the inputs that are on or off, and so in that case this works really well. So every memory only updates a small subset of entries inside of this W, and this is exactly like writing multiple transparent images on top of each other. So uh, if the images are different enough, we can easily see in the overlay of those images where that what that pattern is. And that's sort of the broad intuition. And because each memory is stored in a different direction in a vector space, this is like arrows pointing in maybe east or north or up or diagonal, and that again helps store patterns or memory inside of this weight matrix W. So if we think of, if we put if these input vectors that we just saw, if they are orthogonal, if these input vectors are orthogonal, then each memory occupies its own dimensions, because later we'll see these derivations where if we have input pi, if we dot that with pj, so this is something that is already in the weight matrix. This is something uh, that is, let's say we are trying to um, test or look for pattern. If a dot product of that is 0, this means that the memory 1 goes into dimension 1, memory 2 goes into dimension 2, and so on. So because that is the case and I is not equal to j, we can easily extract information. So let's say here this T is our target and P is our input, and we'll talk about this in more detail later on. But just to example, how does W store each memory? I just wanted to talk about this before that the video where we discuss the actual the linear associator. So let's say we have a W which is a big transparent plastic, right? And so memory one uh, paints a certain picture of numbers onto it, and let's call that picture looks like this, T1 P1 transpose. Then memory 2 paints another picture that looks something like this. Memory 3 paints another picture on the same transparent plastic that looks something like this: T3 P3 transpose. So if all patterns fall in different places, that's if they are orthogonality, that's what we are talking about, then none of them overwrite each other. And so the total sheet, that is the W that we have, so the total sheet, the W that we have, it shows us all the layers. And now if we want to recall something, if you suppose if we have some input that we want to use to recall what is the associated output with that, it can be done. And because this pk that we have would match with something that's already in there, and we can check that uh, by looking at the dot product as we saw there, with p of p, that's already something in there with p of q. And so what this, if pk matches the memory q inside, so this is q, if, and this is k, if this pk matches the memory q that's already inside the weight matrix, then the dot product of this p transpose pq transpose pk is large, and something like 1. And if it does not match, then the product dot product is 0. That's if it's orthogonal. So what this does is it wakes up only one memory, and that's like a shining flashlight through the transparency sheet, which sort of lights up the pattern that lines up with uh, the input that we have, and that's the only thing that glows in that particular sheet, transparent sheet that we have. So this is how this is sort of the intuition behind storing patterns inside a weight matrix and then using a test input to sort of match with the existing pattern that's already inside of the weight matrix to get a expected output. Now you're probably thinking, hey, but wouldn't that create a mess if you have a bunch of numbers, you are just adding them together and putting them in the weight matrix? How is that supposed to keep the patterns separate? And that is a really good question, because we are not going to think about this input from the machine learning perspective that we are used to, where we have columns with different numbers, and rows are our samples. What we are going to think here is inputs that are simply on or off, zeros or ones, or -1, or normalized values. So in those cases, we are also making another assumption where if the input vectors, if they are orthogonal to each other, then each time we put a each time we add the outer product of t with p in the weight matrix, it puts itself in that weight matrix in as a vector in a new direction. Because it is orthogonal, it's always going to be a new direction for each of those uh, outer products that we add in the weight matrix. And that's the analogy where we are looking at multiple patterns on the same transparent sheet of w, and that's where we shine a light. The pattern that is like an input pattern, it will shine, it will eliminate only the pattern that is in the same direction as that input. And so if you're probably asking, what happens if the input vectors are not orthogonal? Does that create a problem? And it does in a way. So what will happen is, if your input pattern is nowhere to be found in that weight matrix, or there's nothing similar to that in the weight matrix, then it will still give us the output, but that output may not be exactly what we are hoping for. And so the value of t that we have, or the vector t, would be in a slightly different direction than what we were hoping it to be in a specific direction, and so there would be an associated error with that predicted output. And so that is sort of the general insight about how, so this is what, how memory is stored in the weight matrix, in the weight matrix. So that's kind of the key idea that we need to remember before we get into the conceptual details and the algebra of how a linear associator works.